So what we got here is I'm going to use a pH meter this time to measure my pH. When you store a pH meter probe, you always keep it, you never let it dry out. It's a very delicate, thin glass bulb that ions have to be able to transport over, and that's how it works. And so you always store it in a buffer solution, usually a little bit acidic, because basic solutions will erode glass eventually. So that's what you're seeing on there right now. It's in a buffer solution. The readout of that pH meter is over there. So we are starting with something that's 1 molar.
Actually, how about water?
Water. Ah. Bring water. It goes basic real quick. Water, you've seen that, right? I concentrated as I saw the numbers of clean for distilled water on that. Okay, thought experiment. Distilled water. I put a drop of base in it. What happens to the pH? It goes up a lot, real quick. No buffering capacity. Y'all know that. Saved us some time, too. Yeah, it's the water. It's the simple stuff we did, right?
That's right.
So we're going to go with 1 molar acetic and 1 molar sodium acetate. So first thing I'm going to do is get my probe ready to go here, which means I take off the buffer solution that it's stored in and rinse it.
So what I wanted to, I'll just point out on this table while he's doing that. So our first buffer solution, we have 1 molar of each of them, so our ratio in the Henderson-Hausbach equation would be 1. So 1 to 1 on that, and a 1 molar concentration on the solution. So what we want to do is see what its initial pH is, and then what happens when we add the base.
So I'm going to add about 50 milliliters to it. Get it to stirring. Just to make it colorful, we're going to add some universal indicator too. And then we're going to put our pH meter in. And close. Oh, whoa! Get out of there.
Wow, 4.74 right on the dot.
Yep.
So what should it be for acetic acid? For acetic acid acetate buffer system, if our ratio is 1 to 1, so the log of 1 is 0, pH equals pKa. Do you remember from all the calculations we've done what the pKa for acetic acid is? 4.74. So you did that pretty well.
Okay. So I'm going to add 2 milliliters of sodium hydroxide to this. Strong base.
Boring.
I know, right?
What if you added more?
What if we added 8 more milliliters to make it a total of 10?
Okay.
Still boring.
Still pretty boring.
Well, yeah, because it's got a pretty good buffer capacity. We added a pretty good chunk of base there, and it didn't change very much.
No. No. So that's with 1 molar components. 1-1 ratio and 1 molar of each. So our last clicker question was, which is better, a stronger concentration or a weaker one? So now we're going to try the same thing, 1-1 ratio, but it's only going to be 10th molar.
And
See how well it does.
See which one has the larger buffer capacity. Which one can withstand more sodium hydroxide without changing pH as much. So now here I've got some 0.1 molar, 0.1 molar, about the same amount, 50 milliliters. indicator. Put our pH meter in. .74 again.
It's the same pH. How come it's the same pH if we have a tenth as much of each component?
Mathematically, why is it the same pH? Same ratio. That's right. The log of the ratio is the same. So it's going to, and it happens to be 0, so it's
pH still equals pKa.
pH still equals pKa, even though we've got less of this stuff. Now we're going to do the same thing. I'm going to add a 2 milliliter aliquot of sodium hydroxide. That's fancy chemistry for aliquot. It means a bit. A little bit more of a change. I still think it did its job. If this was in water, we'd been way over it. 12 or 14 or something. Probably.
Yeah, I think it's still
It changed more, but it's still doing the job of buffering. Now let's add another 8 milliliters of sodium hydroxide. Oops. I broke it.
Yep, you broke it, Randy.
I broke it. Still going. 13.2. And it's still going. Call it.
So what he did was he overwhelmed the buffer, or he exceeded the buffer capacity. So buffers are great, but at some point you can overwhelm. Everything is reactive in terms of the buffering ability, and then it's no longer a buffer. So I think we pretty clearly demonstrated that the more concentrated it is, the better buffer it's going to be. But we've also said that if it's the closer the ratio is to 1 to 1, the better buffer it's going to be. So we want to try one more. In this case, instead of being 1 to 1, it's 1,000 to 1. So what do you think that's going to do? Is it going to be a buffer? Will the initial pH be 4.74? Well, we're predicting no on that, Randy.
That's the prediction, eh?
It's a prediction.
Look on hypothesis. Okay. Wherever are going? Did I rinse that? I don't think so. Yeah. Thank you. Somebody's paying attention. A little bit of indicator. Okay, it's a little bit too fast. Easy to tell.
It's a different color, so I guess we can tell already it's not the same pH. So do you think it's going to be more acidic or more basic?
I heard acidic.
Acidic?
What is it?
It's more basic.
Because the ratio isn't 1 to 1 anymore. It's 1,000.
Yeah, so you should be able to.
You should. Quite.
Yeah. And what it's doing is you stir it, it's incorporating a little CO2, which makes it a little more acidic. So it's.
Okay, so should we try putting some base in it?
Yeah. Let's see if it'll work as a buffer at all.
Okay, we're going to add 2 milliliters of sodium hydroxide.
So was our solution a very good buffer? No. So just because we have a conjugate acid-base pair present doesn't mean it's going to be a buffer. We have to So, pH meters don't like it when it gets really, really basic, so, or really,
And-
really acidic. So we'll
Particularly basic, glass doesn't like strong bases.
particularly when what
But glass doesn't like strong bases.
glass doesn't like strong bases either. Okay.
Or acids.
So let's see if we can get things back where we need them to be here.